Hey guys, this is the second video for the notes for lesson 10.1. It is now my kids' bedtime, so I'm hoping nobody comes down to interrupt me, but I make no promises. I'm on page 194 in case you went to do the assignment in the meantime, and I'm going to talk about the conditions for estimating mu. Most of them are the same. Just like with proportions, there's a lot of things that you still have to meet. So the random condition is not going to change. We still have to make sure we have a random sample. And if you're randomly sampling, meaning you're not doing some type of an experiment, then the only way that you can view your observations as independent is if you meet the 10% condition. Therefore, our standard deviation formula will be fine. And then the last condition is the new one. That's just what it's saying here. The last condition is the new one because we need basically a large counts condition replacement. And you can't use large counts because that's always n times p, and that's for proportions. And obviously, we're not dealing with proportions. So what we are going to be checking is the normal / large sample condition. It doesn't have as nice of a ring to it, honestly, but it's what we're going to be using. So with this condition, we are going to rely on what we had done back in the day. I don't even remember what time of year it was this semester for the two ways we know about the distribution of the sampling distribution of sample means of X bars. So one of the things we said is if your sample size was small, which we had said was 30, your X bars are going to resemble the population shape. So what we're going to do is we're going to look at our sample size and say, is it plausible? Would we be not surprised if this data looks normal? So basically, we're looking for no indication of really strong skewness in either direction. We don't want that. And we don't want any outliers in our sample. Because if you see those, it means you're probably keeping some of your parent population shape, and it shouldn't be normal. So as long as you don't see skewness, you don't see outliers, then you could say, yeah, I would think it's plausible that it came from a normal population. And so check, that's one way to check it. That's the normal, I don't know why I crossed it out, the normal sample part of this condition. The one that's much easier to check is the large sample part of this condition. And if your sample size is large, which remember was the threshold of 30, as long as you have n is greater than or equal to 30, you can proceed. You can use T star for your critical value, and it's going to just be fine. This is true even if the population distribution is specifically stated not to be normal. You get to say, don't care, sample size is large, move on. So there are two ways to check this that we're going to be adding to our list of our conditions. So to summarize, random condition, not going away. If you sample without replacement from a finite population, you got to make sure that that sample size is less than 10% the population size. And then the new one is normal / large sample. So it's just kind of summarized here a little more succinctly. Either the population has a normal distribution or the sample size is large. Now, if the population distribution has an unknown shape and your sample size is small, we're going to graph the sample data to assess normality. So let's look at what this will look like in practice, and then we'll be done. We're going to just check the normal large sample condition because we are really good at the others. So part A. To determine the average GPA of students at your school, you randomly select 50 students. Here is a histogram of their GPAs that I don't want you to look at, because the moment you see that you have randomly selected 50 students, you are going to have a large sample. So yes, we have met this condition because the sample size is large. The sample size, and by large, I mean n is 50, which is a number that is at least 30. You don't have to care about graphs regardless. So even if it said, and the population is skewed right or whatever, it won't matter. You're going to you're going to meet it because of that sample size. So let's move on. Part B. How much force does it take to pull wood apart? The stem plot shows the force in pounds required to pull a piece of Douglas fir apart for each of 20 randomly selected pieces. Now, right there, we have a small sample size. So we're going to have to be cautious here. We are not guaranteed to meet the normal / large sample condition. So the next thing we need to look at is, what do we know about the population? and I know nothing. So our last bet is to look at the sample that was collected. And unfortunately, this sample is really strongly skewed left. That tail is pulled to those smaller values. So we're going to say, no, we don't meet these conditions. Sample size is small, and the sample distribution, the stem plot, displays really strong skewness. I hear one of my children walking around. Let's see if I can finish this video before they discover where I am in the house. Last one in this section was suppose that you want to estimate the mean SAT math score at a large high school. Here's a box plot of the SAT math scores for a random sample of 20 students. Yet again, pay attention to your sample size. We might be in the exact same situation as last time. But now we have to care about the shape. Now here's kind of an issue. It's hard to tell shape for sure because remember with this, we know that 25% of the data is here and 25% is here, but this seems pretty differently spread out. Maybe, but maybe only like 2 are here. Maybe it's equally spread, whereas here, like we don't actually know where these dots lie is the thing. So there is some skewness because if you look for the median and go to the minimum, we would say, well, I'm going to think that's 525. I don't remember. I'm pretty sure this is a range of around 150 for the lower half. And if you go to the upper half, this is about 250. This is me estimating. It's slightly skewed. What's key, though, is there are no outliers. Box plots would show an outlier if there were any outliers, and there are none. So if there's only slight skewness, you're going to kind of say, well, it's close enough. So we're going to say, yes, we meet this condition. I don't know why I said but. Since the box plot is only slightly skewed right, and there are no outliers. Now I know this whole idea of like, well, why is that one only slightly skewed? How do you know when we're talking extreme skewness versus only slight skewness? And I get that that's a frustrating kind of go by your gut, which is not usually a math thing. But there's a note down here for one way to judge skewness. And this is what I was looking at earlier. One way to go is from the maximum to the median, and then the median to the minimum. And if you actually compare that for these two groups, if you go the minimum to the median, which probably is 319, that's a pretty big range. And if you go from that median to the maximum, that's a much smaller range. Specifically, it was calculated 16.5 versus 89.5. So there's a really big difference. One is like 5 times more than the other. But in the SAT example, that 250 and 150, that right half is less than twice as long as the left half. It's really not that different when you're comparing it in that way, kind of coming up with more, like if I double this distance, I'm not quite to 250. So that's one way to kind of quantify it. And I know that's not great. There is not an accepted rule of thumb for identifying strong skewness. So I will make sure that I'm going to avoid those borderline cases. It should be obvious if it's intending to be skewed or if we're just going to meet it with a sample size of 30, which is, like I said, always my favorite way. So at this point, you should be empowered to do the last 2 problems off the assignment, which is just checking these conditions, really focusing in on this new normal/large sample. Good luck.